So let's get started with part 2 of these unit notes, chapter 4, covalent compounds. And so we're going to start looking at how to name covalent compounds. And so on this page you see a table of common prefixes. And so these, with covalent compounds, we use prefixes to tell how many of each atom. So unlike ionic compounds where you had to balance charges, here we are going to use prefixes to tell how many. There are no charges involved with covalent compounds. There are no ions because they're sharing those electrons. And so this table would be important for you to commit to memory. Hopefully some of these prefixes are familiar to you, maybe from just some common shapes. Some common things that you're familiar with. For example, the prefix for 3, tri. We all started out riding a tricycle, probably, with 3 wheels. Penta, pentagon, and a hexagon, those are some common shapes. So these prefixes indicate the number. Here are 2 examples given. Notice the NO2. We can recognize it as a covalent compound because it starts with a nonmetal. Nitrogen is a nonmetal. And so we have to name it as such. So we have nitrogen dioxide, and the prefix di is used because there are 2 oxygen. The second example here, we have N2O4. So we see that we have 2 nitrogens, so we're going to call it dinitrogen. And then tetraoxide, tetra is the prefix for 4. So let's look at a little more closely about how to name covalent compounds. So again, we're going to use prefixes to show the number of atoms present. The prefixes come from the table that I showed you above, table 4.1. The prefix mono is usually omitted when only 1 atom of the first element is present. So we typically never use mono with the first element, but it is retained for the second element. So anytime you have a covalent compound and only 1 of the second element, you would use the prefix mono. So for example, if we had CO, there's only 1 carbon, but we would not say monocarbon, it would just simply be carbon. And then for the oxygen, since there's only 1 oxygen, we name that monoxide, carbon monoxide. Sometimes you run into a problem where there are 2 vowels next to each other. The general rule is to omit the first vowel. And so we see this in the name given here. Monoxide, there's a vowel that ends mono and a vowel that starts oxide, so we simply just drop the first vowel. So you'll have some practice naming covalent compounds as you go along, and again you just use the prefixes that are given in the table above. Alright, along with names, you need to be familiar with the shape of covalent compounds, and we've talked a little bit about the Lewis structure, and we know that the Lewis structure tells us which atoms are connected to each other, but it doesn't show anything about the shape of the atom. And so to determine the shape around a given atom, first you must determine how many groups surround the atom. So how many groups surround the atom? A group is either an atom or it could be a lone pair of electrons. Remember, lone pair of electrons are the electrons that are not involved in the bond. So we're usually looking at the central atom, and we want to determine how many atoms are around the central atom or how many lone pairs. And then we're going to use something called the valence shell electron pair repulsion theory, or it's pronounced VESPER for short, just using the first letters, VESPER theory. And that's going to help us determine the shape. So the most stable arrangement keeps the groups as far away from each other as possible. Just as the name implies, it says valence shell, electron pair repulsion. And so there is some repulsion between the electrons, either the bonded electrons or the lone pair electrons. And so a molecule will typically take the shape in which these atoms or lone pairs are as far away as possible. So on this slide it gives us some examples of different shapes that you're responsible for knowing. It says an atom surrounded by two groups is always going to be linear. So in this example here we have the central atom in red, and then we have two bonded atoms on each side. And so the central atom is surrounded by two atoms, and that takes on a linear shape. The greatest distance that these two atoms can have from each other would be 180 degrees, and the shape is called linear. If you have an atom that is surrounded by three groups, as we see here, then the shape is called trigonal planar. Trigonal planar. So we have again the central atom in red, and there are three atoms around the central atom, and the configuration that puts these three atoms as far away from each other as possible is the shape you see here, trigonal planar, where you have 120 degrees between the bonded atoms. And then finally we have a shape with four groups, and this shape is called tetrahedral, and the bond angle between the atoms is 109.5. So you may notice that the drawing here is trying to show you some three-dimensional shape on a two-dimensional plane, and so the wedge here that is filled in is in a different location than the wedge that is dotted here. They're just trying to show you that one atom is back behind and the other atom is out in front, trying to show you three dimensions. Sometimes that is difficult to draw, and so these wedges are used to show the three dimensions. The next slide can be very helpful to you. You are given some common molecular shapes. These are the 5 shapes that you need to be able to recognize. And we see the 3 that we just talked about, linear, trigonal planar, and tetrahedral. And then it introduces 2 more shapes, one being trigonal pyramidal. And notice there are 5 groups around the central atom. 3 of those groups are bonded atoms, and 1 group is a lone pair. And so the fact that there's a lone pair instead of a bonded atom, the shape takes on a slightly different configuration. So instead of tetrahedral, this is called trigonal pyramidal, and the bond angle would be less than the 109.5. And then finally our last shape here is bent, and notice that bent has 4 groups around the central atom. 2 of those groups are atoms, and 2 of those groups are lone pairs. And again, it changes the bond angle. Whenever there's lone pair electrons, it decreases the bond angle, and the shape here is called bent. So water is a prime example of a molecule that has a bent shape. In Alex this week you're going to be doing a lab that introduces you to some of these shapes, and so this table might become very helpful to you. Alright, let's move along. So any atom surrounded by only 2 groups, again, is linear and has a bond angle of 180 degrees. So we see some different variations. You could just have the single bonded atoms. You could have 2 double bonded atoms, as in CO2. It also forms a linear shape. You ignore the bonds when predicting the geometry, and you count only atoms and lone pairs. So it doesn't matter if it's a single bond or double bond, a triple bond, that doesn't change the shape. So only count the atoms and the lone pairs. So any atom surrounded by 3 groups is trigonal planar, and it has a bond angle of 120 degrees. So again, it doesn't matter if they're single bonds or double bonds, as long as the atom is surrounded by 3 groups, then you get the trigonal planar shape. Here are 3 other examples. And then we have a situation where the atom is surrounded by 4 groups. The shape is said to be tetrahedral, and the bond angle is 109.5 degrees. So Alright, so when we're talking about 4 groups around an atom, if the 4 groups around the atom include 1 lone pair, then we say that the geometry is trigonal pyramidal with a bond angle of 107 degrees. And so here we see an example, NH3. When you draw the Lewis structure, you see their central atom is nitrogen. It's surrounded by 4 groups, but one of the 4 groups is a lone pair. So the lone pair actually takes up more room than the bonded atoms, and so that changes the shape just slightly. And so instead of tetrahedral, you end up with trigonal pyramidal, and that reduces the bond angle. We can also have 4 groups around the atom, but you might have 2 lone pairs, as we saw with our example with water earlier. This geometry is said to be bent, and the bond angle is 105 degrees. So with 2 lone pairs, we see that it shrinks the bond angle even more. And so we have what's called a bent shape. And if you look at this ball and stick model, you can see how they came up with the name. It appears to be bent. All right, let's discuss a little bit about electronegativity. So electronegativity is a measure of an atom's attraction for electrons in a bond. Remember, a bond is made of 2 electrons, and there are certain atoms that have a stronger attraction for those electrons in the bond, and they are said to have a high electronegativity. So electronegativity is another one of the periodic trends that we see on the periodic table, and this picture here below shows the trend as you move from left to right across the periodic table, across a period, the electronegativity increases, and as you move from bottom to top, the electronegativity increases. The abbreviation for electronegativity is capital E, lowercase n. One important thing to make note of is fluorine. So this periodic table, this section of the periodic table, shows you electronegativity values. So you notice that they've removed the average atomic mass and have placed numbers here instead. There is a scale that measures electronegativity, and it goes from 0 to 4, 4 being the highest. And if you notice, the element fluorine has the highest electronegativity value. And so if you'll just keep that in mind as you're thinking about electronegativity, that will help you to make some comparisons. the closer an element is to fluorine, the more electronegativity, or the more electronegative that element is. So we see here, if the electronegativities of two bonded atoms are equal or very similar, then we say that the bond is nonpolar. So when we look at some electronegativity values on the periodic table, for example, they have a C and a C. If we look at the value here for carbon, it's 2.5. And so we can take those electronegativity values and subtract them from each other to find the difference in electronegativity. And of course, the difference between C and C would be 0. And so in this case, their values are equal, and therefore this is a nonpolar bond. If we look at C and H, we see carbon's 2.6, where hydrogen's 2.2. And when we subtract those values, we see that there's a difference of 0.4. And so that's very close to being 0, so this is also considered a nonpolar bond. In a nonpolar bond, the electrons are shared equally between the atoms. Neither atom has a stronger pull for the electrons, so they are shared equally. So this is considered a nonpolar covalent bond. However, we can look at some other compounds, and we see that there is a bigger difference between the electronegativities. So bonding between atoms with different electronegativity values yields a polar covalent bond. A polar covalent bond. Sometimes this is referred to as the element or the molecule having a dipole, which is a partial separation of charges. So the electrons in the bond are unequally shared, in this case between the carbon and the oxygen. Electrons are pulled toward the oxygen, which is the more electronegative element, and we indicate this with a special symbol. So notice this fancy looking S here. I tend to draw it kind of like that. This is a Greek letter. This is the delta symbol, lowercase delta symbol in the Greek alphabet. And this particular symbol indicates a partial charge. Partial charge. And so when we have a polar covalent compound, we have to show where the partial charges are. So in this case, because oxygen has a higher electronegativity than carbon, substantially higher, the electrons in the bond are pulled closer to oxygen, and that gives oxygen a slightly negative charge. As the electrons are pulled away from carbon in this case, the less electronegative element, this is indicated by the slightly positive symbol. So for this compound, CO, for this bond right here between C and O, this side of the oxygen side of the bond is going to be slightly negative because the electrons in the bond are pulled closer to oxygen, and the carbon side of the bond is going to be slightly positive because of the lack of electrons there. And so there is another symbol here shown as a dipole moment is what this symbol is called, and it is just another way of representing where the electron attraction is. And so you have this arrow, and it's showing that the electrons are pulled closer to the oxygen atom and away from the carbon atom. So this creates what's called a polar covalent bond. So here's a full table of electronegativity values. And you can see the range all the way from the smaller numbers on this side of the periodic table all the way to the highest number, which is on this side of the periodic table, so it almost runs at a diagonal. And so when you want to determine what type of bond you have, you will simply take a look at these values, the values between two elements, and you will subtract their values and look at their differences. If the difference is less than 0.5 units, then we say it is a nonpolar bond, and those electrons are shared equally. If the difference is greater than 2 units, then we call that an ionic bond. And we know in ionic bonds that electrons are transferred from the less electronegative, which would be the metal, to the more electronegative, which would be the nonmetal. And so instead of partial charges, we would end up with full charges when that electron's transferred and creates the ion. If the difference is somewhere between the 0.5 and the 2 units, then we call that a polar covalent bond. And the electrons are unequally shared. They're pulled toward the more electronegative element, and that's where we give our partial charges. So we have a partial negative would go on the element with the highest electronegativity value. A partial positive would go on the element with the lowest the lowest electronegativity value. And you can also draw what's called a dipole moment, which is an arrow with a little cross at the end. And it is always going to point toward the element that has the higher electronegativity value, the slightly negative. And this little plus sign right here reminds me of a positive, and so the slightly positive part of the atom would be at this end of dipole moment. All right, let's look a little closer at polarity. The classification of a molecule as polar or nonpolar depends on the polarity of the individual bonds. And it also depends on the overall shape of the molecule. So the polarity of the individual bonds and the overall shape. With covalent compounds that have more than one covalent bond, the shape of the molecule determines polarity. So if the individual dipoles do not cancel, then the molecule is polar. If the individual bond dipoles cancel one another, then the molecule is nonpolar. So a quick example, let's see what we have. Now let's look at the next page for some examples. It says to determine the polarity of a molecule with 2 or more polar bonds, first you want to identify all polar bonds based on electronegativity differences. And then you want to determine the shape around the individual atoms by counting the groups. And then you want to decide if the dipoles cancel each other or they reinforce each other. So let's take a look at some of their examples here. We have a carbon as a central atom, double bonded to the oxygen. And when we looked at electronegativity values, we know that oxygen has a higher electronegativity value than carbon. So this particular bond that we see here, this bond right here, is a polar bond. We can also see by the dipole moment being drawn here, these two bonds, this bond and this bond, are nonpolar bonds. We saw earlier that the difference between carbon's electronegativity value and hydrogen was 0.4, which is very close to 0. So those two bonds are nonpolar. However, the C double bond O is polar. And so we have one dipole moment here, and it is pulling away from the carbon. So we see that this is a polar bond. and therefore we have a polar molecule. All right, let's take a look at another example. We have BF3 here. Each individual bond, this bond is a polar bond, this is a polar bond, and this is a polar bond. And we would know that by looking at the electronegativity differences. When we draw our dipole moments, we would draw them facing the fluorine, because fluorine is the most electronegative element of the two between fluorine and boron. When we look at all three of our dipoles, we see that they're all pulling in opposite directions, and so all the dipoles cancel each other out. There's no net dipole, and so this molecule is said to be nonpolar. It has three polar bonds, but the overall molecule is nonpolar. Let's take a look at this example. This is NH3. Nitrogen has a higher electronegativity than hydrogen. And so notice that we have three polar bonds here, and all of the dipoles are pointing toward nitrogen. And so the dipoles are said to reinforce each other, which creates a polar molecule. Another indication of polarity would be this lone pair of electrons. So once you've drawn your Lewis structure, if you see that there is a lone pair of electrons on the central atom, you're going to have a polar molecule. Our last example here is carbon as your central atom. We have two polar bonds between carbon and chlorine. The dipoles are pointing towards chlorine, and so we have two polar bonds. The two dipoles reinforce one another, and so therefore we have the net dipole. And so it's showing here the net dipole in green. If you think about these dipole moments as being a vector is a symbol that shows direction and the direction of the force. And so if we were to add these two vectors together, we could see that the net force is in the direction of this green arrow. Another way to tell that this is a polar molecule is to look at the central atom and to see what groups are attached to that central atom. And anytime you have different atoms, so here we have hydrogen, Cl, and Cl, we know that there is an electronegativity difference between Cl and C, and so that's going to give us a polar compound. If we had had a molecule that's like this, carbon in the middle with Cl all the way around, well, in this case the dipoles would cancel each other because all of the atoms around carbon are identical, and so this would be nonpolar. So just to recap a bit, to determine polarity, you would want to draw the Lewis structure and look at the shape of the molecule based on the Lewis structure. And then you also want to consult the electronegativity differences. Two easy ways to tell if a molecule is polar or not is, number one, look to see if there's a lone pair of electrons on the central atom, and if so, then the molecule is polar. The second way to determine it is to look to see what is attached to the central atom. If the atoms or groups that are attached are all the same, then you have a nonpolar molecule. But if they are different, then the molecule will be polar. So we'll see a little later on the importance of polar molecules and what they can do for us in chemistry. They're a very important set of molecules. So it is important that you learn how to tell if a molecule is polar or not. All right, that's all for this recording. So you will be practicing naming and writing formulas for covalent compounds, as well as drawing Lewis structures and identifying shapes.